Hi class, welcome back to the continuation of our lectures in electrodynamics. And again, our reference for this lecture is Introduction to Electrodynamics by David J. Griffiths. And this book is highly recommended for you to help you in your study on these topics. So we were left hanging last time as we did not discuss the next example that's supposed to be discussed. So let's now discuss so let's now discuss 3.4, example 3.4. But let's go back to example 3.3 first. So in this example, we had sheets, conducting sheets. Like for example, this one here, the configuration was composed of three sheets. One of uh, one of the sheets was on the side here. One of the sheets was here on this side, the top side and the bottom side. There is no sheet here, metal sheet. So that's a different configuration to the next example. So in this case, by the way, the y-axis is there is boundary on the y-axis below and at the top. On the x-axis, you have a boundary on the left side and there's no boundary on the right side. Of course, the z-axis has no boundary on both sides. So let's proceed with the previous example. With the next example. This is example 3.34. Example 3.34. Here you have two infinitely long grounded metal plates. I'll just read it. Again, at y equal to 0 and at y equal to a here. And they are connected by metal strips at x equal to negative b and positive b, maintained at potential v sub o. Grounded metal plates maintains a potential of 0. A thin layer of insulation in each corner. This is not comer, but it's corner. Corner prevents them from shorting out. So it has to be insulated with an. It has to be insulated so that there will be no short circuit, or they will not be shorted. So here, find the potential inside the resulting rectangular pipe. So the rectangular pipe are all made of conductors. So it's supposed that inside there will be no charge contained, because all excess charge will have to be contained or will have to be distributed on the surface of the configuration. So let's find the potential inside the resulting rectangular pipe. And since there's no charge inside, we have to use the Laplace's equation, wherein wherein V is equal to 0. But if there are charges present, then this 0, then it would not be 0. It would have to be rho over epsilon sub O, negative. So let's proceed. So here you have, by the way, before we proceed, you have a Z that's unbounded. So this one extends to the Z-axis on both sides, the positive and negative Z-axis. So the solution, once again, we have to solve the Laplace's equation that is dependent on x and y. Here, this one. Because it doesn't depend, the configuration doesn't depend on z. So we have this. And it has to fit in the boundary condition, which is at y is equal to 0, the potential is 0. At y equals to a, the potential is 0. At x equal to b, the potential is v sub o. And at x equal to negative b, the potential is v sub o. The same arguments run as in the previous problem. Why? Because here we have, it's independent of z, so we're just looking at x and y. You have a boundary condition on y and also in x. In this case, you will have a boundary condition on the x with the value v. V is not equal to 0. We value v sub o. While on the y axis, the boundary is equal to 0. So it's good to have the sinusoidal solutions to be assigned on the y-axis, because the sine and cosine can go to 0. And it's good to assign the exponential solution because the exponential here does not go to 0. It can only approach 0, but it doesn't go to 0. Well, at x equals b, it's not 0. It's v sub o. So if we go back, let's see, if just to refresh your memory, we go back. We go back here. When we did separable solution, we write vxy as the product of the function x of x and y of y. And we replaced v with x times y here, so we had this equation. And then we rearrange them by dividing the function x y on both terms, and on the right side 0, that we have to make this y this form. Now we have a function, this is a function of f of x only and y only. If these are two functions of different variables and they add up to 0, then by some theory in calculus, that you can only say that this function is equal to a constant and the other one is also equal to a constant. And of course, they should be equal in magnitude but opposite in sign to sum up to 0. In this case, we can let this one and this one as our constant, but they have to add up to 0. And of course, with the look of the differential equation, it's a second order differential equation. We can set the constant to be k square and negative k square. They add up to 0, but they are assigned here for x because x is bounded here, k square, and this one for the y, um both sides are bounded, so we have to assign negative k. In this case, x is only bounded at one side, so that you can assign the positive k. In this case, your negative k square, the differential equation with negative k square, will have a solution of sinusoidal waves, and this one will have a solution that's exponential in nature. So the partial differential equation has been converted into ordinary differential equations. Look here, you have ordinary differential equation because they are now just functions of one variable here. Y is just a function of one variable. So we now go back to our problem 3.4. I mean the example 3.4. Here you have a boundary on the y-axis and on the x-axis, not on the z-axis. But we have to assign the the exponential solution to x because, as you can see, the configuration is symmetric on x but not symmetric on y. So that's also the thing you have to consider when assigning the solutions to the differential equations. You have to see the symmetry and also the boundary of the configuration. So in this case, you have a boundary not equal to 0, and so you have the exponential is suited for that, but it's also symmetric there. So the k squared can also be assigned to this differential equation. So again, we set v equal to x of x and y of y. And replace this v here and then divide everything by xy on this side and also on this side. Also on this side xy. So that you will have two differential equations with solutions of exponential and sinusoidal, because one of them, the k square, will give an exponential solution and the negative k square will have a sinusoidal solution. This is the sinusoidal solution and this is the exponential solution. Now, what we can see here is that the configuration or the potential in the configuration is symmetric with respect to x, because at x negative and x positive, the potential is equal to v sub o. So you have equal potential at negative x and at x. But on y, You have v equal to 0 only at y equal to 0 and y is equal to a. In this case, because there is symmetry between negative x and x, you can set uh, a to be equal to b, because anyway they are symmetric. In this case also, in this case also, your a is not equal to 0, unlike in example 3.3. It's not 0 since the region in question does not extend to infinity. So we have an exponential solution to be an acceptable solution there. So here you can set a equal to b because it is symmetric. The k and the negative k here will have the same value at x equals positive negative b. So you can write this one as this one you can write as some constant, since you can choose a e to the kx plus e to the negative kx over 2 over 2. You can multiply 2 here. By the way, this one here is equal to this. It's just the hyperbolic cosine of kx. And we can absorb 2a into the constants c and d. And for the third boundary condition, for the first and the second boundary condition, for the second and the first boundary condition, the potential must go to 0 when y is equal to a and y is equal to 0. So if your y is equal to 0, your y is equal to 0, the sine will go to 0, but the cosine will go to 1. So how can you make this equal to 0? So you have to let d to be equal to 0. So in that case, you're only left with this one here. So you're only left with the sine in the sinusoidal solution. Therefore, you have the solution. You have the solution vxy to be c cosine n pi x over a sine n pi y over a, because this is now 0. So now we can take a little further. What happens now? Here you have for n equals 1, you have a solution that is a solution. N equals 2 also, n equals 3, and so on. So those are also potential, because n here could be anything as k in the fourth boundary condition. K is equal to n pi over a, such that the sine, because sine has to go to 0, you have sine ky equal to 0, and the only way that this ky, since the potential at y equals a, that is sine ka equals 0, the only way to arrive at this 0 is for ka to be equal to an integer multiple of pi. So that you have many solutions. You have many potential. You can set the potential to be n equals 1, but not n equal to 0, because n equal to 0 will be meaningless, because that would be sine 0 here. So it's not meaningful. So you can have n equals 2, n equals 3, and so on. So you can therefore construct a general solution by constructing a general linear combination of the solutions. So here you have this Cn, we just set this to be Cn, which is a constant for the nth solution. So you can have, so this is now equal to actually C1 plus cosine hyperbolic of pi x over a sine pi y over a plus C2 cosine hyperbolic of 2 pi x over a times sine 2 pi y over a plus C3 cosine hyperbolic of 3 n pi x over a sine 3 pi y over a, and so on. But the Cn there is the coefficient of the coefficient of the coefficient of each solution, each of the elements in the linear solution, general linear combination of the solutions. So we have to find that Cn. So now we can find it. We have to get Cn. So at x equal to b, you uh, have to set x equal to b. This one is equal to VO. So therefore, this one is this one, and of course that one. This one is equal to VO at x equal to b. So you have to set this x as b, so that you have a series that is Cn cosine hyperbolic of n pi b over a sine sine n pi y over a. Note here that if you integrate, let's go back to this, how the Cn were arrived, and it was by Fourier's trick that the Cn's were arrived. Here we did this. So we set the boundary condition that at x equal to 0, here we set equal to 0. This is in example number 3. We set x equal to 0, so everything goes to 1. Everything goes to 1 here, so that you're left with Cn and n pi y over a. And to get Cn, you have to integrate this by Fourier's trick, so that you multiply this one to this and integrate from 0 to a dy. You will have also this one, you have to multiply with this factor, and you also have to integrate that with also to integrate that with 0 to a. The same is here. By the way, the summation and the integration are can be exchanged. They're interchangeable because they mean the same thing, integration and summation. Only that this one is discrete and this one is continuous. Um, continuous summation. So we go back. This is a long one, but let's go to the details of this. So now in this case you have the Fourier streak here. You can multiply this with sine n prime pi y over a, and also here you have to multiply sine n prime y over a, and then integrate. We also have to integrate here with respect to dy and with respect to dy, such that you will have this solution for Cn cosine n pi b over a. You will have this by seeing this equation in the previous lecture. So we can now find Cn, and Cn would just be equal to 4 b sub o over n pi divided by cosine hyperbolic of n pi b over a. So that's the solution. So finally you will have a potential that is of this form. So that is the solution for that. It's raining hard right now. And if you plot this potential in the computer, you will see a beautiful plot, a three-dimensional plot on the V divided by B sub O. You will have a plot here, and if you want to view it on this side, you can also see this beautifully like this. Yeah, I think it's in the next example, but let's now look at the next example. An infinitely long rectangular metal pipe, sides A and B, is grounded. So that means the potential is equal to 0. But one end is maintained at a specified potential VOYZ as indicated in figure 3.22. Find the potential inside. Again, the potential inside is 0 because there's no charge inside. So here you have, in this case, the z-axis is bounded. You have a boundary here and a boundary at the back for the z. The y has a boundary up and down. The z doesn't have a symmetric boundary, and also the y doesn't have a symmetric boundary. The x-axis does not have a boundary here. It extends to infinity here, but it has a boundary on this side at uh, x equal to 0. It has a boundary. So we can set the boundary conditions to be at v at y equal to 0 and y equal to a, v is equal to 0, and then at z equal to 0 and z is equal to b, v is equal to 0, and then at x equal to 0, v is equal to v0 yz, and at infinity, the potential goes to 0 in this case here. This is z equal to b, and this is z equal to 0. This is y equal to 0, and this is y is equal to a. And this one is, of course, this one is, of course, x equal to 0. X is equal to 0. So those are the boundary condition. And x to infinity would be this one. X to infinity would that be. So in this case, the boundaries exist in all the axes. So you are going to solve the Laplace's equation in 3 dimensions. Here. You have two boundaries here, two boundaries here, and sorry. You have two boundaries here and two boundaries here. And for this one, you only have one boundary. The other one is infinity. So you can choose the exponential solution here. And this one are the sinusoidal solutions. Sinusoidal solutions for these two. Because they have non-symmetric boundary conditions. So we can again set the potential to be this, and then we have if we substitute this potential to here, and then we divide everything by x, y, z, we will have this differential equation. Now it becomes an ordinary differential equation, unlike here you have a partial differential equation because v here is actually a function of x, y, z, and this one here are just functions of z. For example, is just a function of z. So it follows that we have this because this is now just a function of x, function of y, function of z, and so they are all constants, and that all of them will just add up to 0. So we can set this to be k square, negative k square, and this one is negative l square, and then you have positive k squared per s plus l squared here because this is exponential. So by the way, take note of this is just another notation for exponential. So we can set the solutions for x to be this one and exponential solutions, and then for the for the y and z you have sinusoidal solutions. But again, you have a equal to 0. I mean, let's go to boundary condition 1. This one will have to be 0 because it's supposed to be 0 at y equals a. But if you put here a, cosine ka is a number, ka is a number, and cosine ka should be equal to 0, and cosine ka will not be 0, so you have to set d equal to 0 to make it 0. And then of course the same argument goes for this part, so f should also be equal to 0. And here also you have to set a equal to 0, because at infinity, x at infinity, this should be 0. Now a has to be set to 0, so that's why you have this as your as the consequence of the boundary conditions. And the second and the fourth boundary condition requires that k is equal to n pi and l is equal to m pi over b. K is equal to n pi over a. So combining everything, so we now put everything in the potential, we will have this. So we will have that solution. And again, in this case, you have n, you have m as the determinant of your constant c. So it's dependent now on uh, two numbers, n and m. So therefore, you can write a general linear combination, and it will be a double sum of n and sum of m. So here's the form of your general linear combination solution. So that's it. That's the solution. And how would you find now this one, C and M? Again, you will use the Fourier trick to do that. Here you have to multiply. Here you have to multiply sine n prime pi y over a, and then for here you have to multiply sine m prime z over b pi there, so that you have an identity, the integral identity for this, and then you will be able to find c and m. And of course this would be at uh, the integral for here should be from 0 to a for the y, and this one is from 0 to b for the z. So let's now set x equal to 0, x equal to 0 here, for x equal to 0 you will have this potential, and that for x equal to 0, this, the whole thing here becomes 1, so it disappears in this expression. So to determine the constant, again, as I've said, you have to multiply this one and this one here will have an identity integral for that, and of course the other side should also be multiplied by that sine and sine, and so you will have finally c, and this one will have uh, will have 2 over a, no, a over 2, and this one will have the same, but it's just b. Let's look at the identity again. It's this integral. It's a over 2 for that, and so if you have b here, b, then it would be b here. So anyway, that's so finally we have this. So you can write this one as a over 2 and this one as b over 2, so that your cm will be this, and that you can also find this one. This one would just reduce also to this one. If your VO is constant in y and z, you can take VO out. This one you can, if that is constant, you can take that out of the integral and just have the integral to be this. So your C and M would just be this, and this one has the conditions that M and N should be add, and for N even or M even, it will be 0. So finally our potential would now be in this form. It's so beautiful to look at. And now if we can see, you can actually plot this in the computer in your computational class and see how beautiful the potential looks like. You also have problems here, which I can show you and take a screenshot of that. And yeah, there's a figure of the problem. You can take a screenshot. And then we'll now go to the spherical coordinates. We were discussing about Laplace's equation in Cartesian coordinates. Now we will go to spherical coordinates. So Laplace's equation in spherical coordinates is this one here. It's a function of r, a function of theta, and a function of phi. But a function of phi potential would be very, very complicated, and it has a solution, a very long solution, I mean, so that if we can reserve this um, this potential that is dependent on phi to be to be when you take advanced physics course. So you can also see problems or discussions with potentials dependent on the azimuthal angle, the phi. So, but here in our discussions, we'll just take the radial and the polar dependence, the r and the theta. Of course, the r and the theta here. So for that, we will assume that everything has azimuthal symmetry, so that we can only have this differential equation. So we will assume that it has azimuthal symmetry, so that we can write our potential to be r of r, theta of theta. And putting this to here, putting this to this equation, this is the Laplace's equation again, but in spherical coordinates. And let's go back. This is actually familiar to you. In chapter 1 we have this, so you don't have to really worry about this. This looks complicated, but it's just the same as the Cartesian coordinates, just converted into spherical coordinates. And here, so when you substitute, you can separate everything, all functions of r and all functions of theta, and you will be able to reach this expression. And then of course these two would have to be constant, and so you can set this as the constant, and this one is the other constant, and so they have to sum up to 0, and then you have the solution for the radial component of the differential equation. You have this solution. So if you get the derivative of r, look at this derivative of r with respect to r. This is just um, derivative of r with respect to r. This is just equal to L times a, r to the L minus 1 plus b minus b minus L minus 1 minus L minus 1 times b r to the L minus 2. And then if you multiply this with r squared, this will become L plus 1, and this will become r to the L. This will become r to the L. And if you derive it, you will get this expression. Again, if you get the derivative with respect to r, then you will get this expression, because like L times L plus 1, and then here you have L plus 1 times negative L. This is negative L, sorry. Negative L, so that's still L times L plus 1. And you will get this expression also, so that you will have this as the result. So that's the solution, exactly the solution. So this is the solution for R, radial part. And unlike in the Cartesian coordinates, you have sinusoidal solution and exponential solution, but here you have a different form of solution. For the angular part or the polar part and the theta part, you also have this. You also have this solution. So we have this differential equation, and the solution is the Legendre polynomial. We have discussed Legendre polynomial earlier, right? Or no? Maybe in my other class I have discussed this solution. This differential equation is special because its solution is called a special function or special polynomial called Legendre polynomial, and the this Legendre polynomial PL is generated by the Rodriguez formula, this one here. But of course, in electrodynamics, x would be equal to cosine theta. So like this one would be cosine square theta minus 1, and that would just be what? Negative 1 minus a plus sine theta also. Or this is just equal to sine theta, sine square theta, this one here. So for by the way, 1 you can write that as sine square theta plus cosine square theta. So anyway, that is the solution for the for this differential equation. This one you will encounter in quantum mechanics, this differential equation. But for now, let's just accept that the solution for this one is Legendre polynomial. You can ask your teacher in mathematical physics to discuss Legendre polynomials, so that you will know the details of this solution to this differential equation. So these are the first few Legendre polynomials. P0 of x will just be 1. This one is just P1 cosine theta equal to cosine theta. You can change cosine theta with x, or x with cosine theta, I mean. So you have here listed up to P5. Here the factor in front, 1 over 2 1 over 2 L to the L times L factorial was chosen so that P1 P1 PL1 is equal to 1. Here's a note here. Equation 3.60 is a second order differential equation. This one is a second order differential equation. But The other solution will blow up at x equal to 0 and theta equal to 0 and theta is equal to pi. So we will not discuss that solution. We only discuss the Legendre polynomial as it is uh, the physically acceptable solutions for physics. So we don't, of course, in mathematics you can discuss that, but in physics we only discuss um, physical solutions. So we will not discuss that second solution. This is one of the solutions there. This is one solution, but we will not discuss that. So our solution in the spherical coordinate system, the solution for the Laplace's equation is this one, this form. This is the r of r, and this is the theta of theta. So it's much easier. We don't have to find other solutions. We can only use this one. So let's now take the examples. By the way, L is of course running from 0 to 1, 2, 3, and so on. So we will have a general solution, which is a linear combination of all the separable solutions. So L starts from 0 here. So let's now look at example 3.6. The potential V sub O theta is specified on the surface of a hollow sphere. Hollow sphere means it's a spherical shell. It's a spherical shell of radius r. Find the potential inside the sphere. So inside the sphere would be r is less than the radius. So inside, r can go to 0, and outside, r can go to infinity. So here v should be 0 at infinity. So if this is infinity, inside, if r goes to 0 inside, this one would go to 0. So it's okay. This one, if it goes to 0, this one will go to infinity. The whole thing will go to infinity. So we have to let BL equal to 0. This one, if inside. So we will now have only this potential. So at r equals r, or the radius, the potential is equal to V0 theta. So that V r theta now becomes ALR. Now the r is becomes the big R because it's now at the surface, or the surface has a potential V sub O. So your potential would now look like this. And the Legendre polynomial, if you know, is a complete set of functions on the interval -1 to 1 for x and 0 to pi for theta. So if you use the cosine theta, you have to use this limit, and if you use x inside as the argument of the Legendre polynomial, you use this limit for the Legendre polynomial. And it has an identity that if you integrate two Legendre polynomials here, you will have 0 if L prime is not equal to L, and 2 over 2L plus 1 if L is equal to L prime. Now let's do this. So how do we get A? The question here is what is A? R is just a constant. Of course, PL is this is the Legendre polynomial. We will now get A. So we will now multiply here PL prime, and this one also PL prime, and then integrate with respect to cosine theta, and then here also integrate with respect to d cosine theta, because that is the argument of the Legendre polynomial, which is this one. So you have to put sine theta here and sine theta, of course, because that's how to integrate the theta. You have to put sine theta d cosine theta. No, I'm sorry. This is already I already put the cosine theta here, so it's not needed. The sine theta is not needed. The sine theta here is not needed. It's already d cosine theta, so it's okay, because d cosine theta is already equal to sine theta d theta negative. So anyway, that's what you have to do. That's the Fourier trick for this. And so your A L prime R L prime, this would now become 2 over 2L plus 1, and this is just equal to 0 to pi V sub O theta PL prime cosine theta sine theta d theta, so that your AL would be equal to this. So how do you get, for example, if you have, for instance, if you have V sub O theta equals K sine squared theta over 2, where K is a constant. So you can write this as, you can write by using some trigonometric identity, you can write this as K over 2 1 minus cosine theta, or you can, 1 is just PO cosine theta, and cosine theta would just be P1 cosine theta in our listed Legendre polynomial above, so that your VR, if you put this here, that's just an example. If you put this here, your K sine squared theta, if you put that there, sine squared theta over 2, if you put that there, you will find out that your potential would just be equal to this, because this one this one would just be this one would just be what? This is just a1 or a0 p0 cosine theta plus a1 r to the 1 p1 cosine theta plus a3 a2 r to the 2 p2 cosine theta, and so on. So you can then compare p0 and p1 with that, and so your potential will just be this one. So you don't have to really do Fourier strict in that case, because that is already given. If you have some potential like this, but if not, you have to do some other calculations for that. So the next example would be the potential V0 theta is again specified on the surface of a sphere of radius r, but this time we are asked to find the potential outside, assuming there is no charge there. So in this case, the AL must be 0, because AL will have R to the L, but outside R can go to infinity, and this one will have to go to infinity, so we have to set AL to be 0, so that we're left with only the B, only that one. And at the surface, where R, the small r is equal to R, we will have this. Again, we can find BL by doing the Fourier strict as above. We can find the BL to be equal to this one. So it's a little faster now. So that's it. You can of course you can, if this is specified, like for example, if this is k times sine square theta over 2, then you can always find the coefficients BL. So you can explore example 3.6 and then find out for 3.7. It's just an extension. Now for 3.8, here we have an uncharged metal sphere of radius r placed in a uniform electric field E equal to EOZ, so it's in direction Z. The field will push positive charge to the northern surface of the sphere, leaving a negative charge on the southern surface of the sphere. This induced charge in turn distorts the field in the neighborhood of the sphere. Find the potential in the region outside the sphere. So initially the sphere is an equipotential, and it will stay an equipotential for forever. This can be an equipotential which can be set. This equipotential is a constant, but we can set the potential to be 0 at the surface. So then, by symmetry, the entire xy plane is at potential 0. The entire xy plane here, xy plane is equal to 0. Here you have the boundary condition is that v does not go to 0 at large c. In fact, at large c, the potential will just be this one, E0 or E sub O times negative E sub O times z plus some constant. So anyway, this constant will be the potential at inside the sphere, but we set that to be 0 at the surface, so this can be 0. So we have now the boundary conditions of the problem to be v is equal to 0 when r is equal to r, and it approaches to e o r cosine theta for r greater than r. R cosine theta is just equal to z. This is just equal to z. So z, so anywhere here, z would just be, if this is theta, this is just, this is theta, that is the spherical coordinate. The orientation of the theta is, here, so z would just be cosine theta. So anyway, let's make the figure bigger. So if you have here a point and you're measuring r here, and this is the theta for the polar orientation, and so this z here, this will also be theta, and so your z would just be r cosine theta. Cosine theta. So that's the boundary condition. So the first condition yields that the v is 0 when r is equal to r. So when the r here becomes r, this is equal to 0. So we can say that BL is equal to negative ALR to 2L plus 1. So we can write the potential to be this. We can write the potential to be that. And for R greater than R, the summation, the potential, for R greater than R, B is of course equal to 0. And so you will have this to be equal to that. And evidently here you have only L equals 1, because PL1 cosine theta is equal to cosine theta, which is this one. So R to the 1 is just equal to R, and E1 is equal to negative E0. So the conclusion is that we have a potential that is equal to this. You only have L equals 1. So we just look at this as the solution and then find the coefficients. So we just look at this as the solution and then we find the coefficients that will satisfy this solution or the boundary conditions. Then That's already the solution then. So that's how the logic goes for this spherical coordinates. So then we will now go to so again here we have a solution for inside the sphere, and of course the one outside the sphere. But again, we're just doing for the problem. We're just doing the sphere out. I mean the potential, finding the potential outside. So how can we uh, get the charge density outside this or on the surface of the sphere? We just use again this formula. In this case, our normal unit vector is in the direction r, so we have to use the radial component, and then we can find by integrating the potential here. By integrating the potential, we can find then the induced charge on the surface. The the northern part will have positive charge and the southern part will have a negative charge. That's why the electric field, if there were no charge induced in the surface, the electric field would have just a straight line, would only have straight line. But in this case, since this is a conductor, the positive charge will concentrate at the top here, and the negative charge will concentrate. That's why the electric field are distorted here. You can see that there is a distortion. If there were no charge, then it would just be straight lines. So that's for that problem. And then we go to this is now the last problem before we end the session. So at specified charge density theta, sigma is glued over surface of a spherical shell of radius r. Find the potential inside and outside the sphere. So you could do the integration by doing this. I mean, finding the potential by doing that. We have done this before. However, it would be easier to use the potential from the separable solution in terms of spherical coordinates. So inside the sphere, which is r less than r, or the radius, we only use AL because of course B is equal to 0 because it blows up inside the sphere as it goes to the origin. And for the region outside the sphere, we have this. No AL terms because it will blow up as r goes to infinity. So at the boundary r equals r, these two would have to be equal. And so that if these are equal, then we can cancel this, and this one we can cancel. But it's not ordinary cancellation. We just can say that they can cancel, but you have to do the Fourier strict to cancel that. So we have BL is actually equal to AL times r to the 2L plus 1. And the second derivative, the first derivative of the potential should be continuous, but we have a charge on the boundary, so the continuity is disturbed by that charge distribution. So the potential, the first derivative of the potential, or the electric field out outside the sphere and inside the sphere, is discontinuous. And in this case, the field outside, this is the derivative of the potential, and the field inside would have a discontinuity equal to that. And we discussed that previously in the previous classes that we had. So using this, we have the potential outside and the potential inside. And this is just equal to that. And this is just the derivative of the potential. And so we have this one finally. You can combine the summation. And of course, we have, doing the Fourier trick, we can find AL. We can multiply PL prime cosine theta on both sides, and then we can find AL. So for instance, if we have, just for example, if we have theta equals k cosine theta, sigma 0, if we have sigma 0 theta equals k cosine theta, then k cosine theta would just be kp1 cosine theta. So you can substitute that here. So p1 p1 cosine square, p integral of pl prime dx is just equal to 2 over 2l plus 1, right? So this is just equal to what? This one is just equal to 2 over 2 times 1 plus 1. So this is 2/3. So that you will have this as the result for A1. So you can do these details on the assessment. So finally, for that charge distribution that we did, we can have this potential for uh, the region inside the sphere, and outside the sphere we can also have this one. So so the so this one, if we could go back to 3.8, you can see that these are consistent with that. So that's what you have to do in the assessment. And you have some problems here. You can try when you have time. You can take a screenshot of that. And of course, these additional problems, you can take a screenshot also. And then we have this one. You can screenshot and then read them. So the next lecture would be on multipole expansion, and I hope you've learned about separable solutions of the Laplace's equation which enables us to calculate potential in terms of Cartesian coordinates and spherical coordinates. So just um, understand the examples by heart, and when you encounter difficult problems, you will you'll be confident to solve them. So that's all for this lecture. I will I will just post the assessment in our Google Classroom. See you.